Yeah, so thanks to the organizers for inviting me. So today I will talk about two tools that basically help to design various one-shot quantum communication protocols. And the two tools are one is what we call the convex-split lemma, and the other is called position-based decoding. Okay, so this is joint work with Anurag and Vamsi, and this is with okay, and two are basically kind of complementary and dual to each other. One helps in encoding and the other helps in decoding. Okay? So what is the convex-split lemma, right? All right, so let's say we have the following a convex combination of states. Okay? So what we have here is rho p q1, okay, and we have here sigma q2, sigma qn, and we here rho pq. Let me just say rho pq. And we have sigma q1, q3, oh, okay, all right. Okay, sure, yeah. Okay. Okay, so basically we have this convex combination of states, right? So what are these states? So we take a state rho, say on two registers PQ, and it's in the first two registers here, and then the state sigma. Okay, so this is all in tensor. Okay, and we have several copies of sigma in tensor. Okay, this is the first state. The second state is the state rho is in the first and the third site. Second site has sigma, and fourth onwards all has sigma. Okay, and similarly in the nth state, we have rho in the first and the nth site, and all the other sites have sigma. Okay? So, all right. So, if we consider such a convex mixture, okay, then the convex-split lemma says that if n is large enough, okay, which is related to the Dmax of rho pq with rho p tensored sigma q, then this state, okay, is equivalent to is close to rho p tensored sigma okay. All right. Okay, so is the statement sort of clear that if we consider this convex combination where n is large enough, so I'll precisely state what n needs to be, then this convex combination is pretty much the same as a decoupled state with rho p here and just sigmas everywhere else. Okay?
There must be some relation between rho and sigma for this to hold, right? Otherwise, it's actually false.
No, so I'll specify how large n has to be.
Let's say you take rho pq to be just 1, 1 and sigma to be 0, then the first n states have 2 1s, whereas the last state has just 1, 1, so you can distinguish those two.
No, but then the Dmax should not be infinite. I mean, it has to be in the support.
Good, so there's some condition on Dmax.
Yeah, I'm giving the condition. So, okay, so if this is the state, then the statement is, so let's call this entire state on the left hand side this as a tau, okay, state tau. So then the thing is that, so let k, maybe I'll just talk about this on the other side of the board. Okay, so let k be equal to Dmax of rho pq with rho p tensored sigma q. Okay. So by the way, all these sigma q2 all the same state sigma. Okay. So yeah. So okay, and then let me also say what is Dmax. So Dmax is defined to be minimum over C such that rho pq is less than 2 to the C times rho p tensored sigma q, where this is the loner order, right, for states. Okay, so that's Dmax, and let's say we have k is that, then the relative entropy, okay, relative entropy between tau, okay, and tau p, but tau p is the same as rho p tensored sigma q1 qn, which is the state on the right hand side, is less than or equal to log 1 plus 2 to the k over n. Okay? Right? Oh, write it bigger? Oh, write bigger? Okay. So if we take n to be larger than 2 to the k, right, say 1 over epsilon times 2 to the k or something, so then we get, you know, sort of log 1 plus epsilon here, which becomes epsilon. Okay, so small. So then this is for relative entropy, and then via, you know, Pinsker we can go to, say, fidelity or something. Yeah.
And it's not true for Dmax.
Okay, so we have a converse for Dmax, but there, you know, but the statement we only show for D though.
Okay.
Yeah.
So I mean, is it?
Yeah, okay, for Dmax.
Like, is it false for Dmax, or just you don't have to prove it for Dmax?
Okay, so we have not considered showing it for Dmax,
Yeah.
but okay, my guess would be that it is false for Dmax.
Because it's just, you know, striking that you know the condition you start with is Dmax and
Yeah.
you end with one about D.
Yeah, yeah. Yeah, although the converse we are only able to show for Dmax.
But I guess if it's a D, which would be the more relevant one, because that would take us to the phase distance.
Yeah, exactly. That's true. That's true. Okay. So let me just state. So via Pinsker we go to fidelity, and that says okay. All right. Okay, so so this is a convex split, and okay, so the position-based decoding is sort of the dual picture. Okay, so then what there the question is that you know, once you have a mixture of this kind, okay, then can you, given this mixture, reproduce? So let's say that there is a correlated index j here, right? Correlated random variable j, which, you know, is I if we have the ith component of the mixture, right? So now, you know, so if we trace out j, we know that this is the state decoupled, right? But now the question is, if you're given this state, then can you recover j? Okay, recover j. So that is related to, so since this is related to Dmax, and the recovery is related to dh. Okay, so basically, let me just, you know, not draw the diagram again, and just say that, you know, you can recover j as long as n is like the dh of. So let me just sort of informally say here, recover j is possible as long as n is, say, order dh of rho pq with rho p tends to sigma q. Okay, and dh is, yeah, I mean, again, you know, sorry. Recovery up to error epsilon, sort of, or order epsilon, and dh epsilon is defined to be this hypothesis testing divergence, which is okay, so we have this maximum over C such that, write it here, C such that there exists an operator, measurement operator M, such that your success on rho PQ is high, and your success on rho P tensor sigma Q is small. Okay? All right? So,
what's the quality of recovery of J? With what error?
yeah, order epsilon, sort of, or epsilon square.
That's the probability of error. That is the probability of error.
Yeah, yeah. Sorry, order square root epsilon, actually. Okay? All right. So these are the two tools that we use to design various quantum communication protocols. So maybe let me just mention the applications that we have obtained, and then I'll get into the proofs of these things. Okay, so for message compression kind of situations, we can get new. So these help us to design sort of new one-shot protocols, and we can get for single sender, single receiver, setting, commonly known as quantum state redistribution. Okay, and the subtask of these like quantum state merging, state splitting, and so on. Okay, then two sender, one receiver. And the time reversed version of it, which is one sender, two receiver. This is commonly known as quantum slip involve. Then for measurement compression, this is essentially sort of state redistribution with classical message. State redistribution, classical message, and classical shared randomness. So rest of it is still quantum. So it's quantum state redistribution with classical message and classical shared randomness. And then, so this is for the just the ideal channel setting, no noise, and for the noisy channel, the regular point-to-point channel. So here we get optimal bounds in the one-shot setting with known converse. Broadcast channel. I mean, this is the Martin's bound setting. Then Gelfand-Pinsker channel. Yeah, this is a channel where there is a side information of the channel with the encoder. Then compound channel. This is like, here a channel is chosen adversarially from a given set of channels. Okay. Then Mark has has considered private channels where Eve gets no information. So about the message being sent. Okay. Okay. And then I guess Mark and co-authors also have considered they have been able to obtain some error exponents and second order asymptotics for point-to-point channel. And also some connections between multiple access channel and multi-hypothesis testing. Yeah.
The 4 surprises me because 4 is the only one which is not IID, right? Because the compound channel has memory. So
Yeah. Okay. Yeah. So for that we have to show one additional thing, which is some kind of a quantum OR result, like bounding the probability of kind of an OR of 2 events. So there's one additional thing that we have to show there. Yeah. Sorry, non-IID, but these are all non-IID. I mean, so these are all one-shot results. All one-shot results, which actually do imply non-IID results. Okay, and then there have been some other sort of miscellaneous applications also obtained. One is in quantifying noise for resource destruction. Anuragan. Then there is basically a version of sort of a weak operator Chernoff can be obtained using this, which is only polynomially. I mean, the consideration is only polynomially fast, not exponentially fast. So then there's something port-based teleportation. And so this is also, I mean, part of this is also done by Berta and this is catalytic decoupling. Okay. All right. So, I mean, basically, a few applications have been found of these two tools, and so we expect more to be found, especially in the design of quantum network communication protocols. Okay. So let me sorry, it's just 10 minutes left? Or?
15 minutes since we started a bit late.
Oh, 15 minutes? Okay. All right. So let me try to at least do the proof of convex split. Okay, so the proof is actually relatively quite simple, and so first is that there is a lemma which is also quite simple, which says that suppose we have a convex combination of states which gives us this average state, and there is another state theta, right? Then the relative entropy between mu and theta is equal to summation over I pi relative entropy of mu I with theta minus relative entropy of mu I with mu. Okay? And this is just the proof is like direct calculation. Okay, we just open the definitions of relative entropy on both sides, and the terms cancel, and we have this. By the way, I never wrote a definition for D, but definition for D is trace rho log rho minus trace rho log sigma. Okay. So let's say we have that, and now we can just consider the calculation. So we have d of tau p q1 to qn rho p tensor sigma. So rho p is the same as tau p, so That's the same. So then this lemma tells us it's the same as 1 over n summation over j d rho pq j tensor sigma minus j. Okay, so sigma minus j is basically sigma. Okay, so so let's say that let's define sigma to be sigma 1 tensored, up to sigma n, okay, and sigma minus j is basically all of this where on the jth place sigma is missing, okay. J minus 1 tensored j plus 1, okay. All right. So, all right. Yeah. Okay, so using this, right, we get that since tau is a convex combination, right, of these states, rho p q j with sigma minus j, right. So we have this with with sort of the second argument here, and again the same thing with the first argument, okay, as given by this lemma. So that's what we have, and one thing we can note is that the sigma already has this sigma minus j sitting, right? So we can just get rid of that, and therefore the first term is nothing but, so the first term for each j is nothing but d of rho pq with rho p tensored sigma. What should I say here? This is sigma. Let me call it sigma tilde, which is the bigger one. And yeah, just single copy of sigma is right.
Your starting point.
Yeah, that's true. Okay, right? So this is for every j, it's just simply rho pq with rho p tensored sigma. Okay. And what about this, right? So here we can use the sort of the monotonicity of relative entropy, right? Which will then tell us that this is, so this is equality. So maybe let me just write equality as is for now. Okay, and then what we will have is right. So minus d of rho pq with tau p q j. Okay, so for now let me just write it as minus 1 over n summation over j. Right? So if we just trace out everything else and only keep the jth system and p, right? So what we'll have here is PQ, and what we'll have here is tau PQJ. Okay? All right? And the relative entropy, you know, here will only decrease, but it's a minus sign, so it's going in the right direction. Okay? All right. Okay, so now let's analyze what is this quantity, d of, okay, so then, you know, and from symmetry of things, we can see that, you know, this tau PQJ is actually the same for every j, right? So therefore, it's essentially just, you know, one term here, okay? But let's analyze, so let's analyze rho PQ, let's say with tau PQ1, okay? What is that? All right? Now, one thing we can note is that tau PQ1, right, is 1 over n rho PQ with 1 minus 1 over n rho P tensored sigma q, right? You see, only in one of the components in that mixture we get rho PQ, and in every other component we get rho P tensored sigma q. Okay? So therefore, tau PQ1 is basically this state. But then here is where we can use Dmax, and Dmax is telling us that this is less than equal to, right, 1 over n 2 to the k times sigma, rho P tensored sigma q, right? Okay, so we can use Dmax to upper bound this into by 2 to the k times this, and then we already have this here. So this becomes 1 minus 1 plus 2 to the k minus 1 over n times rho P tensored sigma q. Okay? This is where we use Dmax. All right? And now we are pretty much done, okay? Because now what is this? This is trace rho PQ log rho PQ minus trace rho PQ log rho P, tau PQ1, okay? Which, you know, so we take log on both sides here, and we use the fact that log is operator monotone, okay, which gives us greater than equal to trace rho PQ log rho PQ minus trace rho PQ log rho P tensored sigma q minus log 1 plus 2 to the k minus 1 over n. Okay? But then this is the same as the relative entropy of rho PQ with rho P tensored sigma q. Okay? And now, you know, we can simply substitute it here, right? And each of the term is the same as this, and this term is the same as this, okay? So that just cancels, and we get okay? Yeah, so the proof is relatively simple. You know, it just follows from you know, the data processing for relative entropy, and an operator monotonicity of log, okay, and more or less direct calculations. Okay, so that does that. Now I would have wanted to maybe describe, how we obtain, say, any one of these protocols, say, for stated distribution, or let me quickly give the protocol for point-to-point channel, okay. Okay, just a protocol for point-to-point channel, which is as follows. So let's say we have Alice, okay, and Bob, and Alice has an index, right, say 1 to m, okay, and she wants to send that index to Bob, okay, and there's a channel in between that acts. So what Alice and Bob do is they share a state, let's say, pure state, psi a prime a, several copies of it, okay. Okay, and so here is the channel. Let's say it acts from, A, let me just call it A. Yeah, but A and A are isomorphic, so, and then it goes to B here, okay. So what Alice does is she simply takes, if she wants to transmit I, she simply takes the ith copy of this shared entanglement and feeds it into the channel, okay. All right, and let me call the channel from A prime to B. Okay, so and then what happens is, so conditioned on Alice transmitting I, the state with Bob, is precisely that on the ith location you have your channel, acting on psi a prime a, right? So that's your state in the ith place, and everywhere else, all you have is this local copy of A sitting there, right? So that's just psi A. Okay? So now what Bob has to do is figure out I from such a convex mixture, right? And therefore, position-based decoding. Now, so what is the proof of position-based? So we see, intuitively, we can see that if Alice makes a measurement, if Bob makes a measurement, right, which succeeds very well on this state, okay, but fails, so we are looking at dH epsilon of the channel acting on psi A prime A with, just the marginal of, so channel acting only on psi A prime, tensored just psi A, right? Okay? Right, so this is the state that we have if we look at the first index and any other index other than I. This is the state, and this is the state that we have on the first index and the ith index. Okay? So if Bob has a measurement which succeeds very well on this and fails badly on this, right? Then one can imagine. So there is a renormalization issue, but that gets taken care by the Hayashi-Nakuka inequality. But one can imagine that measurement will then succeed very well. If that measurement is done. I'm just saying this is not formally correct, but let's say sequentially that measurement is done, it will fail and it will succeed on the ith index, conditioned on the state being the state where the correlation is with the ith coordinate. Okay, so anyway, so this is just a very quick picture of why this decoding helps to achieve a rate like this. And of course, this can be done for any state, so then we can maximize over all states psi a prime, right? And this number asymptotically goes to mutual information, and therefore one recovers. Yes, and this is also there's a lower bound known for this due to Stephanie and co-author, and therefore this turns out to be an optimal rate for point-to-point case. Okay, so let me stop here. Any questions?